Okay, hello everyone. Let us continue the third part of today's class. Excuse me. Okay, so figure 4.7 is the notional depiction of a generic time-variant multi-pass impulse response function. Okay, this is the t-axis. Okay, and this is time 0, time t1, time t2, and time t3. Okay, so and this is the tau axis. That is the time relative to the time 0, and time t1, and time t2, and time t3. Okay, this axis is c of t tau. Okay. As you know, it is the impulse response function, okay, which is at time 0, and at time t1, and at time t2, and at time t3. Okay. So, as in the simple example, the t-time dimension corresponds the time dimension over which the channel changes, and the tau dimension corresponds to the time dimension over which the channel responds to an impulse that occurs at a given value of t. Excuse me. In real multi-pass channels, there are usually many scatterers, which results in the impulse response having a continuous appearance in the tau dimension. Okay, like this. Okay, you can see that these impulse response functions are continuous functions in tau. Next, let us go to section 4.4, intrinsic multi-pass channel parameters. There are 4 key parameters used to characterize the intrinsic properties of multi-pass channels. Okay, we have explained what is intrinsic, okay, earlier. Okay. However, on this page, we will introduce the word intrinsic again. Okay, in the viewpoint of communications. Okay, in this context, the word intrinsic means that the parameters refer to the properties inherent in the channel and are not related to the nature of the signal that is being transmitted through the channel. Okay, so what is the parameters which are related to the nature of the signal? Okay, for example, the time duration of the signal, or the bandwidth of the signal. Okay, or the power spectrum density of the signal, okay, etc. Later in this chapter, we consider different ways of characterizing channels based on the relationship between these intrinsic parameters and certain features of the signals being transmitted. 2 of the intrinsic parameters are related to how the multi-pass channel varies in the t dimension, and the other 2 intrinsic parameters are related to variations in the tau dimension. Excuse me. Okay, we begin by considering the 2 parameters that characterize the tau dimension. Okay, so next let us see section 4.4.1, parameters related to tau. The two intrinsic multi-path channel parameters that characterize variations in the tau dimension are delay spread Tm and coherence bandwidth Bc. These parameters are related to the time dispersion properties of the channel. Okay, in general, dispersion refers to dispersing or spreading a signal out in some dimension. Excuse me. Okay, so next point, it is bold and red, so you can know that this point is very important. Okay, time dispersion refers to spreading a signal out in the tau time dimension due to the effects of multipaths. It is important to keep in mind that delay spread and coherence bandwidth do not provide information about the time-varying nature of the channel. That is, the dependence of the channel on T only on its temporal response to an impulse at some instant of time. Okay, next let us go to section 4.4.1.1 delay spread Tm. Okay, relation to channel impulse response. Delay spread is a measure of the range of propagation delays experienced by the multipath components of a signal when transmitted over a time-dispersive multipath channel. The theoretical definition of delay spread is in terms of the autocorrelation of the channel impulse response function C of t tau. Okay, for this purpose, it is typical to assume that the multipath channel is wide-sense stationary WSS in T, okay, which means that the autocorrelation of the channel response at 2 points in time, that is, at 2 values of T, is only a function of the difference between the 2 time instants and not the instants of time themselves. Okay, under this assumption, the autocorrelation function ACF is defined as follows. Okay, phi c of delta t tau 1 tau 2 is defined as 1 over 2 times the expectation of C complex conjugate of T tau 1 times C of T plus delta T tau 2. Okay, please note that there is a constant 1 over 2 and there is a complex conjugate which is taken on the first C function. Okay, where the wide-sense stationary assumption is reflected in the fact that the autocorrelation function is a function of delta t only. Okay, so we can see that the autocorrelation function is a function of delta t only, and it is not a function of T. Okay. So in most wireless channels, the attenuation and phase shift of the channel associated with path delay tau I are uncorrelated with the path associated with tau j, where I is not equal to j. This is called uncorrelated scattering. US. Okay, this is the abbreviation. When a channel is both WSS, okay, that is white sense stationary, and has uncorrelated scattering, it is said to be a WSS-US channel. Okay, that is a white sense stationary and uncorrelated scattering channel. Excuse me. Okay, under this assumption, phi c of delta t tau 1 tau 2 is equal to phi c of delta t tau 1 times delta of tau 1 minus tau 2. Okay, this is because if I is not equal to j, okay, the path delay tau 1 and the path delay tau j, the corresponding attenuation and phase shift are uncorrelated. So we can see that when tau 1 is not equal to tau 2, delta of tau 1 minus tau 2 is equal to 0. So the autocorrelation function is equal to 0. So that is, okay, at tau 1 and tau 2, the attenuation and the phase shifts are uncorrelated. Okay, if we consider a single instant of time t, then delta t is equal to 0. So phi c of delta t tau 1 tau 2 is equal to phi c 0, okay, because now delta t is equal to 0. So delta t can be replaced by 0, and tau 1 times delta of tau 1 minus tau 2. Okay, and we can simply write this equation as phi c of tau. Okay, because this 0 is a constant, so we can omit it, and there is a variable tau 1. Okay, so we can change the variable tau 1 to tau. Okay. Okay, and phi c of tau is equal to 1 over 2 exponential, the expectation of the square of the absolute value of c of tau. Okay, let us go back to equation 4.14. Okay, when delta t is equal to 0, okay, so this is delta t, okay, is equal to 0. So this is t and this is t. Okay, and this is tau 1, this is tau 2. So we can now let tau 1 is equal to tau 2 is equal to tau. Okay, and the autocorrelation function is not a function of t, so we can omit the variable t. So this function becomes c conjugate of tau, and this function becomes c of tau. Okay, so multiplying them together, we get the square of the absolute value of c of tau. So finally, we can get that the autocorrelation function is equal to 1 over 2 times the expectation of the square of the absolute value of c of tau. Okay, where phi c of tau is called the multipath intensity profile, the delay power spectrum, or the power delay profile. Okay, sometimes you see PDP, okay, it means the power delay profile of the channel. Okay, what is the physical meaning of the expectation of the square of the absolute value of c of tau in equation 4.16? Okay, let us go to equation 4.16. Okay, this is equation 4.16. Okay, we are asking a question: what is the physical meaning of this term? Excuse me. Okay, to help answer this question, consider figure 4.8, which depicts the low-pass equivalent input and output of a multi-pass channel in both time and frequency domains. Okay, let us see figure 4.8. Okay, so in figure 4.8, this is the time and frequency domain input-output relationships of a low-pass equivalent multi-pass channel. Okay, so this is the channel input. In time domain, the channel input is small u of t, and in the frequency domain, the channel input is capital U of f. And capital U of f is the Fourier transform of small u of t. And this block denotes the multi-pass channel. The impulse response function is small c of t tau, and the frequency response is capital C of Tf. Capital C of Tf is the Fourier transform of small c of t tau. So you can see that when doing the Fourier transform, the integral, the variable of the integral is tau, not t. Okay, then it is the channel output. The time domain of the channel output is small r of t, and the frequency domain is capital R of f. And capital R of f is the Fourier transform of small r of t. Okay, as with any filter, the relationship between the frequency domain representations of the input and output is given by, okay, capital R of f is equal to capital U of f times capital C of Tf. Okay, so the output signal spectrum is equal to the spectrum of the input signal times the frequency response. Okay, which implies that, okay, take the absolute value of the both sides of this equation and taking square, we have the square of the absolute value of capital R of f is equal to the square of the absolute value of capital U of f times the square of the absolute value of capital C of Tf. Okay, since Parseval's theorem states that the integral from negative infinity to infinity, the square of the absolute value of small r of t dt is equal to the integral from the negative infinity to infinity, the square of the absolute value of capital R of f df. Okay, so Parseval's theorem says that if you want to find the energy of a signal, okay, then you can find it in the time domain, or you can find it in the frequency domain. Okay, the results are equal to each other. So it follows that the total received energy ER, okay, according to the definition of energy, ER is equal to the integral from the negative infinity to infinity of the square of the absolute value of small r of t dt is expressed as, so ER is equal to this integral. And according to the Parseval's theorem, this integral is equal to this integral. And replace this integrand by the equation 4.18. Okay, then we have ER is equal to the integral from negative infinity to infinity, the square of the absolute value of capital U of f times the square of the absolute value of capital C of TF df. Okay, if we assume that the input to the channel is a delta function, then capital U of f is equal to 1. Okay, because we know that a signal, if it is a delta function in the time domain, then after taking the Fourier transform in the frequency domain, it is equal to 1, a constant. So ER is equal to, okay, this is equal to 1. So this term is equal to 1, and we can cancel this term. So ER is equal to the integral from negative infinity to infinity, and the square of the absolute value of capital C of TF df. And according to the Parseval's theorem, it is equal to the integral from negative infinity to infinity, the square of the absolute value of small c of t tau d tau, and this is equal to the integral from infinity to, or from negative infinity to infinity, the square of the absolute value of c of tau d tau. Okay, why can we cancel the variable t here? Okay, because where the third equality holds, because the channel is assumed to be y-sense stationary. Okay, so the autocorrelation function of the channel does not depend on t. Okay, so we can cancel the variable t. Okay, or we can remove the variable t. Since energy has units of the unit of power times the unit of time, okay, that is watt times second. This equation shows that the square of the absolute value of small c of tau is the received power as a function of tau. Okay, because ER is the energy, and the d tau, okay, is a very little amount of time. Okay, so energy is equal to power times time. Okay, so we can know that this term is the power, which is a function of tau. This means that in practice, the multipath intensity profile can be computed by transmitting an impulse and measuring the received power as a function of time. The resulting time-varying function is the multipath intensity profile. Okay, figures 4.9 and 4.10 show examples of measured delay profiles in residential outdoor environments with and without a direct path component. Okay, let us see figure 4.9 first. Okay, figure 4.9 shows an example of a measured multipath delay profile in a residential environment when there is a direct path component combined with scattering. Frequency is 850 megahertz. Okay, it is 25 minutes. See you next time. Goodbye.